Okay, hi and welcome everybody. So pleased Marc Levine give this week's talk in the motivic geometry seminar. His title is Atiyah-Bott localization for Witt-cohomology. Thanks.
Oh, yeah, hello everyone. Thanks for joining. So the basic idea is, so Atiyah-Bott localization and the Bott residue formula is a very useful tool for making computations of characteristic classes when you have a torus action, especially when the torus action has finitely many fixed points on your variety. Then you can reduce the computation of characteristic classes to some representation theory of, say, the bundles that are being looked at the fixed points. And yeah, so it's a useful computational tool. So the idea is to give some kind of quadratic version of that. So where you, instead of getting values in singular cohomology, you get values in a cohomology theory that involves quadratic forms. And that will be Witt-cohomology, so cohomology with coefficients in the Witt-sheaves. That's sort of the simplest type of cohomology theory that has such a character to it, has a quadratic character to it. So yeah, it turns out, well, this is a big little outline. I'll just review the classical Atiyah-Bott localization and Bott residue formula in the T equivariant case. Say a little bit about equivariant Witt-cohomology to set the stage. And then the two main settings where I prove a result about these Witt analogs of the Atiyah-Bott localization are for actions of SL2 to the n and for n to the n. Sorry for the two n's. So n here is the normalizer of the torus, the standard diagonal matrices inside of SL2. Okay, so that's the program. So first of all, so classical Atiyah-Bott localization. So if let's T is going to be our torus, so multiplicative group to the n, and well, and let's like the simplest case. Let me just take GM for example, and then BT is P infinity or CP infinity if you want, and so the equivariant cohomology of a point, that'll just be the usual cohomology of BT. So this is just a power series ring in one variable T, or maybe let's call it E. E is the Euler class or first Chern class of O of 1. Okay, and then of course you can take the n-dimensional torus, and then you get the, you have in each variable, you have the O of 1 from that variable, and that gives you a power series ring. Or things are homogeneous. I think of that as a polynomial ring. It's really the same thing. And now if you have X to be, let's say, a C scheme, if you like, you can assume it's smooth. For the non-smooth case, you have to pass to Borel-Moore homology, but that's a technical point. Let's not worry about that. For X a C scheme with T action, we can use we use the Borel construction for the equivariant cohomology. So this will be so what's this ET? This is sort of the algebraic version of the Borel construction. This will be some, you know, colimit of, you know, AN minus, yeah, AN to the n minus 0. So you have a free T action, and you just take the co-limit, and then this is defined just to be the limit of the cohomology. All right. So, and you have a similar theory for Borel-Moore homology, but as I said, I'm not gonna tell you about it. Okay, so the main thing that makes, so the problem is to compute this. And the idea is after, so of course this is a module over, this is an H star BT module. And the idea is after inverting some elements, P, so this is, you know, essentially a polynomial ring, you look at some positive degree elements in here. This thing reduces to the equivariant cohomology of the fixed points. But since they're fixed, this is just going to be the usual cohomology of the fixed points tensored with the cohomology of the classifying space. So after inverting some elements. So where does this come from? It's pretty simple. So why is this? Well, just take, I mean, you kind of stratify your space by the orbits, and the orbit type remains constant over locally closed subsets of various quotient spaces. So the main point is to look at just to see this kind of vanishing for an orbit. There'll only be finitely many orbit types. So for each orbit type, you're going to get a polynomial you need to invert, and then you just multiply those finitely many together. So for a fixed orbit, the T orbit will just be something of the form X. Let's just say X is just a T orbit. It's going to be X modulo some T modulo some smaller subtorus, and then times some finite subgroup. Here, T0 inside of T is some subtorus. So this subgroup here will have, well, let's assume if the dimension of X is positive, then of course this thing will have will be some very, you know, small subvariety. There'll be lots of characters that vanish on it. One has characters of the torus. Chi, let's say chi a. It's just the function. If you use the usual coordinate functions t1 up to tn for the torus, it'll just be something of the form product of ti to the ai. Characters chi a, non-trivial, that vanish, or in other words, are constant equal to 1 on this subgroup. Okay, and what that tells you, see each character, the character chi a, gives rise to a line bundle. You know, it'd just be the line bundle O of A1 to O of AN on this BT, right, by just descending by the character. And the associated first Chern class of this thing, this will just be the sum of the AI EIs, right, because the Chern class is additive. And the fact that it vanishes, it pulls back to a trivial bundle. So this OA AN pulls back to a trivial bundle on this Borel construction. So this class here, this is like an P here. So P will go to 0 in the equivariant cohomology of X. And of course, if you invert P, so So after inverting P, this cohomology just becomes 0. Okay, and now what you do is you essentially stratify X by essentially by orbit type. This finitely many, and you invert the finitely many P's you need, right, from this construction. And then, so a localization sequence in, say, Borel-Moore, equivariant Borel-Moore homology. I mean, it's really, you can stratify things further so everything is smooth, if you like. It's a technical point. Implies that if you take the inclusion of the fixed points, this induces an isomorphism. Induces an isomorphism.
Sorry, what's the assumption on capital A?
Capital
It's just
A.
anything in X?
Just some finite group. I'm just saying if you have a positive dimensional T orbit, right?
Okay.
Homogeneous space, it'll be T modulo some subgroup that's a proper subgroup. And all the proper subgroups in the torus are going to be a subtorus times some finite group. It's not a product, it's just generated by a subtorus and some finite group.
Great. And the little ai, where do they come from?
Well, so this torus, right, this torus here corresponds to a rational subspace inside of Q to the n, right? That's how you get a subtorus inside of a torus. Just, right, you just have a bunch of equations. And you just take the A1 up to AN that vanishes, if you view it as a dual vector, that vanishes on that subspace. And then due to this finite group here, you may have to multiply them. You know, you clear denominators and you have to multiply by some larger integer. And that will then vanish automatically on A. Like
Thanks,
if you multiply your integer guy by the order of A, that will work. It's a bit of overkill. But you always have lots of these characters, so that's how you get that.
Thanks.
Okay, yeah, thanks for the question. So, right. So that induces an isomorphism in, you know, equivariant cohomology. And that's the localization theorem. That's the Atiyah-Bott localization. Okay, so that's sort of half the story. And now that raises the question, given some element X in your equivariant cohomology, and then how to find some Y in the equivariant cohomology of the fixed points, such that I lower star of Y is equal to X after inverting something. Plus maybe something else, plus something else. Okay, and well, it's pretty easy to do this. The answer is Bott's, I think it's called Bott's residue formula. Yeah, for simplicity, let's assume, just to explain it, let's assume that xt is just a single point. Okay, you can sort of jazz that up a little bit. It's pretty easy, but just for the purpose of exposition, let's just see what happens if it's a single point. Okay, so then you have the normal bundle. You have nx was the normal bundle. Well, of x and x, this is, sorry. This is, of course, I mean, in general, it would be the normal bundle, but the normal bundle is just equal to the tangent bundle at x, right? And since x is a fixed point, the torus acts on this, so you have a t representation. Right, and that then has an Euler class in the cohomology of BT. So you want to also invert, let's also invert this. Now, you have the projection formula. It tells you, let's see, so how does this work? If you suppose you have your, if we know that my x after inverting my p is I lower star of some y, right? For some y in the equivariant cohomology of the fixed points, which is in this case just equal to the, cohomology of BT. Well, okay, so what does that tell me? That tells me that I upper star of x is I upper star, I lower star of y. But then, so deformation to the normal bundle in this case, which is just the tangent bundle, tells me that this is just y times the Euler class of this normal bundle, which is just the tangent bundle. Okay, so that solves for y. Which makes sense once I invert this Euler class. Because I only need to invert it in here, right? Because that's where it's living. So that's the residue formula. It's the formula for the gadget that gives you the thing, right, that tells you I lower star of I star x over x equals x. Okay, now it's even nicer because if let's say x you wanted to compute, if the x you wanted to compute was some Chern class of some equivariant bundle, well, then I upper star of x is just the, so the equivariant bundle, the, right, would be the equivariant Chern class. So the pullback will be the Chern class of the equivariant bundle, but this is now again just something in this is just a T representation. So you just need to know the formula for the Chern classes of T representations to calculate the Chern class of your equivariant bundle. So that's how you use this thing. All right, good. Any questions? Okay, so so the next.
Sorry, Mark, to be slow. I've gotten confused again about the equations cutting out the subtorus and then taking the dual. Could you just give a very simple example? So, GM
Sure.
cross GM and take a subtorus and give me the AIs.
Yeah, so let's take a GM cross GM. And this contains the subtorus of things of the form t squared t cubed, right? That's my T0. I mean, just think of the T's in some algebraically closed field, right? In other words, so what's the equation? So it's the equation you want to look at. So what's the equation? This is the set of all T1, T2, such that T1 cubed equals T2 squared. I think that's right. So that's the dual. So that says the character chi of, in other words, T1 cubed T2 to the minus 2 is equal to 1. So chi 3, oops, my battery is low. Oh dear, that's bad. Well, let me, I don't know what to do about that. Dear, oh dear. So chi 3 minus 2 vanishes. on T0. Okay, so I think I'm gonna, let me just, I'm gonna have to cheat a little bit if we'll tell you some jokes or something. Let me just plug this in temporarily. I'm afraid I don't have another cord. We'll just have to wait a minute, 1 minute.
No problem, we'll wait for you.
I knew there was something I meant to do. So you have a chance to ask another question first, if you have one.
What's your favorite representation in this context that won't be sort of defined over Z? Like I think of a lot of the standard representations of things like SL2 and therefore the normalizer, but I could definitely imagine lots of interesting ones.
They're all defined over Z for a torus.
Okay, I mean, the motivation would be ultimately, we want to compute some more Euler numbers.
Yeah.
And so I don't want to just do things over Z where we're going to know the answers from the real localization and the complex localization. So I was, nosing around for.
That's the beauty of it. The representation theory is all over Z. But the actual examples are on schemes, which there you have things which are, I'll get to it. They're nice.
So they're going to be.
There are twisted forms and interesting things that happen when you look at actions, not representations.
Great. So you're going to get some general formula for the class, for these Euler classes, and then the bundles associated to these representations. But then these bundles themselves won't be defined over Z.
You can do things which are on schemes which aren't just Grassmannians or things like that. I mean, you can have interesting actions. It's when the geometry comes in, you get things of interest.
Great.
That are not just.
But your tori are always split, right?
Yes. This is just a prop. Yeah, I'm not talking about anything more complicated than a product of GMs for this example. Okay, so I'm hopefully a little more charged up. So that's the example. Let's look at the cohomology theory I want to consider. So Witt-sheaf cohomology. So, right, so if you have a ring, then you have the Grothendieck-Witt ring of R. This is just the ring of virtual non-degenerate quadratic forms over R. And this gives you a pre-sheaf. You can sheafify this, and this gives you the sheaf, GW, so a sheaf on, let's say, smooth varieties over our field. Okay, it's a natural functor in that. And then you also have the quotient, the Witt ring, which is equal to the Grothendieck-Witt ring. Well, for a field anyways, it's modulo the so-called metabolic things, but for local rings, it's modulo hyperbolic things. That's all we need. Okay, so that gives you the sheaf of Witt rings. Again, sheaf on smooth varieties over K. So you just take the cohomology, right? You can just take the Znavich cohomology. Gives you a reasonable cohomology theory. And this is then a module over H0. We're talking about things on smooth varieties over K. So on H0 on spec K of W, which is just the Witt ring of K. All right. So that's the basic object. And this is the reason this is interesting, I mean, we're really more interested in the Grothendieck-Witt ring. That's the real interesting object, but at least if, I mean, you have this fiber square, which tells you that the Grothendieck-Witt ring maps by Z to the rank, maps to the Witt ring, and they agree over Z mod 2, because you mod out by the hyperbolic form has rank 2. And so you can recover an element here by knowing its rank and knowing its image in the Witt ring. So you don't really lose too much information by passing from the Grothendieck-Witt ring to the Witt ring. And this has the advantage that it kind of separates out. This rank here is somehow integral or cohomological or singular cohomology information. And you kind of separate that out, and there's a trace of it remaining by looking at things with Z mod 2 coefficients. But the interesting quadratic information is all in the Witt ring. And it just simplifies the story for what happens, say, for Chern classes in the Chow ring, and Chern classes in the Witt ring are very different. And it makes what happens in the Grothendieck-Witt ring rather complicated. So when you separate these two things out, it gets more simple. Okay, and there's also, I should just say, there's a Borel-Moore homology theory. You know, using 6 functors and this, that, and the other thing, but let's ignore that. But let's look at the, now let's say, so you have some group scheme G. So linear algebraic group, some closed subgroup of GLN, a group scheme over K. And we can then consider the G equivariant cohomology with coefficients in the Witt ring. So what you can do for this is you take the Morel-Wojewodsky model for EGLN, which is just, if you like, this will just be the colimit over n by n matrices of maximal rank. And you use this guy. This plays the role of your contractible space with a free GLN action. And you just take the G, it'll also be a contractible space with a free G action. So you can define this guy here, where now X is some scheme with a G action. You define this to be you know, the limit of the cohomology of these. Maybe I call this something, call this UNN of X cross UNN modulo G coefficients in W. Okay, now it turns out.
Mark, is this really due to Totaro?
Yeah, originally this idea was due to Totaro, but then I think Morel and Wojewodsky showed how it works somewhat more generally. Totaro, I think, did this for the Chow ring, and then it got generalized by Edidine and Graham. And I referred to Morel and Wojewodsky because they kind of express this in the unstable homotop, A1 homotopy category. But you're absolutely right, this really goes back to Totaro. Okay. Good. Okay, so you take this gadget, and actually this limit is eventually constant. Very much like what happens for the Chow ring. The Edidine-Graham version of the Chow ring relies on this to be eventually constant. This is a consequence of the Ross-Schmidt resolution for W, which is, anyways.
Isn't that a direct limit?
Yes. No, it's a inverse limit, I think, isn't it? No, because you have restriction maps for the inclusions. As you increase n, you have an inclusion of n by big N matrices of rank n into the larger ones, and then the cohomology restricts under that.
Okay, thanks.
There's a lim1 term vanishing probably.
Yeah, that because it's eventually constant, so the lim1 vanishes. So it makes it a good theory. All right, so there's a Borel-Moore version of this, which has been worked out by my current PhD student, Alessandro D'Angelo. So that's available, and it's useful for the localization argument, but we're not going to say too much about it here as avoided. Okay, so that's the basic gadget. And so we have equivariant Witt-sheaf cohomology to deal with. And now why? Why bother? Well, the main reason is that the cohomology of Bt for a torus with coefficients in the Witt-sheaf is just W of k in degree 0. So all the Euler classes of line bundles vanish in Witt-sheaf cohomology. So the first Chern class of O of 1 is 0. You don't have anything in here. So you don't have anything to invert. So what this says is that the Atiyah-Bott localization fails. You can't do it for torus actions in any reasonable way. So you need some other groups. So what are the let's groups which are groups whose W cohomology, for the classifying space, are like the singular cohomology of Bt include, so the two main suspects are SL2 to the n. So if you think about it, this Witt-sheaf is kind of telling you about the real theory. And if you look at SL2 over the reals, it's a circle, which is just like C star, just like, C star. You view it as a real manifold. So SL2 is a reasonable thing to look at for this theory. The other thing to look at is you take n inside of SL2. This is the normalizer of the usual torus. So this is just this. So if I call this T1, this is the subgroup generated by T1 and an extra element sigma, which is just this, the usual reflection element. Okay, so what about this? Here's the theorem, which is due to Anievsky, that the Witt-cohomology of BSL2 to the n is the Witt group adjoin, n variables here, where let's do for n equals 1. What's this E? This is the Euler class of, let's say, F. F is equal to, A2 with the standard SL2 action representation. Well, maybe I should call it, let's call this thing O tilde of 1, which corresponds to, so if you have this representation, then you get a bundle, which I'll call O tilde of 1 on BS, this is O tilde of 1 on BSL2, corresponding to the standard rank 2 representation of SL2. Okay, and then you do this EI is just the E from the ith factor. Right, you have the pullback projection onto the ith factor, and you pull that back, that gives you EI. So this looks just like the cohomology of BT. Now, the cohomology of Bn, let's just do one factor, is not quite so simple. It's let me put it this way, it's equal to the cohomology of BSL2 for star. Oh, by the way, this is in H2. It's in degree 2. So for star bigger than or equal to 1. So for star equals 1, it's 0. For star equals 2, it's bigger than 2. It's just this polynomial ring in the variable E, and it's a little different. It's a little bigger in H0. And I'm not going to go into that. It's not so useful for us. But what turns out, just for ease of statements in the localization, we're going to invert this guy anyways. This is the same thing as the cohomology of BSL2 with E inverted. So, and the same thing works for the nth power. So if you invert, in this case, we're going to take E to be the product of the EIs. So after inverting this thing, which we're going to be doing anyways, these two gadgets have cohomology, which just looks like cohomology of a torus, except the coefficients is the Witt ring, which is just what we wanted. Okay, so that's the basic gadget. And now we'd like to do, so Atiyah-Bott.
Sorry, Mark, you're going a little fast for me. Could you just scroll up for a second?
Oh, yeah. Sure.
Great, thanks.
Okay, let me hold on a second. It's too much. Give you a little pause. Sorry for this. Sun came out in my eyes. Okay. Okay. Is that okay?
Just a quick question. Are there other interesting groups for which this kind of computation has been done?
Oh yeah. So Anievsky did much more general theories, but if you the so-called SL oriented with eta inverted theories. Okay. So that W is one of them. But he computed the cohomology of SLN, DSLN.
Okay, but for instance, if we take G to be the veil restriction of a split torus on an extension of K.
Oh yeah, that gets complicated.
Okay.
I don't know. So I think once you do anything which is atal trivial, but Zariski non-trivial, it gets complicated.
Okay. Okay, thanks.
Sorry. That's an interesting question, and maybe I have a good answer, but maybe not. Sorry. Any other questions? Yeah, I mean, most of these things you get toward the edge of what you can do with non-trivial forms. It gets difficult, but so you can do something. All right, so let's go on to the Atiyah-Bott localization for SL2 to the n. And here, formally, everything works, except it's no longer true that an arbitrary orbit of positive dimension can be killed by inverting something. So that's the problem. So problem, the cohomology, even for n equals 1, is not killed, not always killed by inverting a p not equal to 0 in the cohomology of, bigger than 1 degree of B SL2 to the N W. I'll give you some examples, but so there are some for which it works. Okay, so that's the idea here is it's sort of, it's not a great theory. I'll jump ahead a little bit to tell you that the theory for n to the n is much better. So there, essentially everything works. That's still a work in progress, but I'll tell you what's available there. It's much nicer situation. All right, so what's the theorem? So here's the basic proposition. It's by no means the full answer. It's just some examples or some types. So let's take G to be SL2 to the N and take X a SL2 homogeneous space over some field K. So what does that mean? It means over the algebraic closure, if you have a point over some extension field, then X is a single orbit. It's a scheme with a G action, and once you have a rational point, it's a single orbit. But you may not have a rational point. And you have the quotient. You can take, the quotient will then be a field. It may be larger than K, so let's take that. Let's say spec Kx is equal to X modulo G. So the quotient will be spec of some field, and that's the sort of field of definition for the quotient space. So suppose let's see, two things. Okay, you have to suppose it has a point. Suppose that X has a K of X rational point. So it's really a homogeneous space. It's really a G mod H over your base field. And secondly, well, let's call it P sub X. And if you take the isotropy group inside of G is contained in a maximal parabolic, so split parabolic of G, so SL2 to the N, or is contained in a maximal, I just made up this name, maximal diagonal subgroup. So what's a maximal diagonal subgroup? You take indices I, j, different, not equal, and you, let's say G, I, j contained in G will be the subgroup scheme of things of the form, G1 up to Gn, such that Gi is equal to Gj. And a maximal subgroup is some G prime, which is conjugate to a Gij for some I and j. Okay, so those are the sort of annoying conditions. But if you have that, then right, then the SL2 to the N cohomology of X, so vanishes after inverting a P not equal to 0 in H star EG W star equal to 1. Okay, so it's not so hard to see. I mean, the idea is, for example, this case, you can assume that the G prime is equal to a Gij, and then what would vanish here is just the difference, EI minus EJ, right? You look at the Euler class for the ith factor, the fundamental representation for the ith factor, and the one for the jth factor. When you restrict to one of these subgroups, of course, they'll be equal. So they'll vanish when you go up to the homogeneous space. And here, in this case, if you have a maximal parabolic, P contained in SL2 to the n, this will map to a P1 coming from one of the factors. And on the P1, your fundamental representation, when you pull back to P1, let's say P1 is just the quotient of one of your SL2s, when you pull back from a point to P1, P1 is just the space of flags inside of the two-dimensional representation. So your two-dimensional representation fits into it, has a one-dimensional subgadget and a one-dimensional quotient. And as I said, the Euler class of a line bundle is 0, but the Euler class in a exact sequence is the term in the middle is the product of the two Euler classes. So that kills the Euler class of that fundamental representation. So that's kind of the reason why that works. Okay, now these things are not completely, it doesn't tell you the general situation. So let me just give you a bad example just to show you why it's not so nice. So here's a bad example.
Sorry, Mark, which Euler class were you talking about right now?
These EIs, remember EI, so you have the this fundamental representation F for SL2, right? It's just a two-dimensional representation.
Mm-hmm.
And oops, again, my battery is dying. And this gives you this bundle O tilde of 1 on BSL2.
Yes.
And the E is the Euler class of this rank 2 bundle on BSL2. And then the EI is the one you get by pulling back from the ith factor. From SL2 to the N, going by the ith projection to SL2. Is that clear?
I mean, I understand which bundle we're talking about, but I'm just, for just a minute, confused about what do you mean by Euler class right now? In which?
Oh, I see. Yeah, I should have said in all these theories, right? You have an Euler class you have an Euler class of a bundle, or a bundle with the trivialized determinant.
Right.
Since it's a 2 representation, it has a canonically trivialized determinant.
Ah, okay, that's what I was missing. Okay, thank you.
Yeah. Okay, so here's the bad example. Let's take, again, we have our standard representation on F. This is a two-dimensional representation. And let's take X to be the projective space on Sim2 of F. So Sim2 of F is now 3-dimensional. So this is a P2 with some SL2 action. And you have a squaring map, goes from P of F. Okay, and the image is some conic inside of this. This is projective space. This is P1, and the image will be some conic inside of here. In fact, it's the conic, if you use coordinates in some natural way, it's the conic given by x1 squared equals 4x0 x2. If you view this thing as symmetric bilinear forms, these are the square symmetric bilinear forms. Okay, so now it turns out, so let's let x0 be x minus this square of this P1. And it turns out this is a single SL2 orbit. So this is your homogeneous space. But it turns out that you can compute it, that the map, I mean, if you just compute the thing and you get that the SL2 equivariant cohomology of this X0, where you invert this E, is actually isomorphic to the cohomology of BSL2 with E inverted. So yeah, you can't really, and you can't really do anything with this. You're never going to get rid of it. So that's a bad example. A good example, so another bad example is you just take non-trivial forms of PGL2. Like SL2 acts on PGL2 because it's just a quotient, it's SL2 mod plus or minus 1. And we all know over certain fields, like over the reals, PGL2 has twisted forms. So they're torsors for PGL2 with no rational points. And that means it'll be a homogeneous space for SL2 without any rational points. So this other condition about having a rational point fails. I wasn't able to make the complete computation of the SL2 equivariant cohomology for a twisted form of PGL2, but at least the Euler class doesn't go to 0 there. It's and I wasn't able to see what happens in a higher degree, but I think it's probably not so good. So yeah, sort of running out of time, I wanted to get to the story about N, but let me just say that a good example, you can take, for example, you take a to the 2n, and this has the obvious action by SL2 to the n, but just the ith factor, you know, the first factor acts on the first 2 coordinates, the second on the next 2 coordinates, etc. And this induces an action of SL2 to the n, acting on Grassmannian of M planes in 2n space. And this has good properties. This is good. Okay, so maybe I'll just say so here's the theorem. If you have SL2 to the n acting on some y, and all orbits are good in the sense that they fall under the rubric of this proposition, then you know, then there exists a p not equal to 0 in the cohomology of B SL2 to the n W, such that the push forward map from the SL2 to the n cohomology of the fixed points is an iso after inverting P. And once you have that, the residue formula is exactly the same. Residue formula holds. But then there's another caveat here. You had to invert the Euler class of the normal bundle, and it could be that that's 0. So again, this action of this example of sim2, in fact, every odd bundle has vanishing Euler characteristic, Euler class. So for example, sim2 is a odd rank vector, odd rank representation. So the Euler class will vanish. If you're on an odd dimensional manifold and you have a isolated fixed point, you're out of luck with this formula. Doesn't help. Okay, so let me, the few remaining minutes, let me just talk about the case of the normalizer of the torus. So we let n again be the subgroup generated by TT inverse in this matrix. And we've already seen that the when we invert this product of Euler classes here, this is the same as this is this gadget here. So maybe I'll just cut to the chase and say that here's the theorem, Atiyah-Bott localization. So maybe I should say that I think it works in general. And this afternoon I was doing the last little bit of work that needed to get the general case to work. But since I haven't quite finished that up, let me say that let Y be a K-scheme with n to the n action, and suppose all the orbits of positive dimension are satisfy one of the following. So the first one is if n equals 1. So then everything works. Now, I should say that this is just like a torus in that if you have a big torus acting on a space, and if the fixed points are finite, then you can take a general one-dimensional torus inside that big torus with the same set of fixed points. And that works just as well here. So if you have an n to the n action with finitely many fixed points, and you take a general n sitting inside there, it will also have finitely many fixed points. So you can usually reduce to this case. But then there are some other cases. Let's say all the orbits are integral and smooth over their, remember I defined this field over the orbit x is integral and smooth over its quotient space. And what was the other one? There was one other condition. Oh, and the other one is it has a rational point. Orbit x has a point, rational point over its field of quotient space. So one of these following, then the Atiyah-Bott localization works. So in other words, there's a non-zero polynomial in the coefficient ring in the bn to the n cohomology. When you invert it, you get an isomorphism going from the fixed points after inverting some p. Okay, and the residue formula is the same. Now, so I'm absolutely out of time. The clock has struck. Let me just say a few wild comments at the end. So first of all, I'm pretty sure that this works. You don't really need these conditions. It really works in general. There's a caveat though, in that in order to apply the residue formula, again, you need a similar condition. You need to know that the Euler class of the normal bundle is non-zero. In the case of a torus, that's always the case because the normal bundle, if you have a trivial representation in the normal bundle, well, then you're not looking at all the fixed points. The trivial representation gives you a tangent direction where you can move to get more fixed points. Now, in this case, in the case of n, you have this extra z mod 4, z mod 2 acting besides the torus. So you could imagine you have to take the fixed point locus for the torus, and then you have a smaller fixed point locus for the sigma action. But then the sigma action will be, you know, a bunch of trivial or sign representations, and that'll be bad. Those will have zero Euler class. But the good news is if the torus already has a finite, has a zero-dimensional fixed point locus, well, adding the z mod 2 action will just select some of those points, and you won't be getting a trivial Euler class. So in those cases, when the torus action actually cuts down the fixed points to 0, you're okay. And the last comment is, what do I mean by fixed point? So this is an interesting case here. Fixed point means set theoretically fixed, means dimension 0, but fixed. So you could have, for example, let's look at the case of n. You have this torus, and then you have this, it really has two components. The group has two connected components. So if the torus acts trivially, it means you have a Z mod 2 action on some point, but it could be acting non-trivially on the residue field. You could be getting a degree 2 extension. So what you need to do there is to compute what is the equivariant cohomology of that kind of gadget. And it turns out to be pretty amusing. It's not the Witt ring of the field, it's the Witt ring of the field modulo the image of the trace map from the Witt ring of the degree 2 extension. Now, in the case of the reals, and you have a non-trivial extension, you're taking the complexes over the reals, and the trace map on the Witt rings is 0. So you're not losing any information. In general, you'll be losing a little bit of information. Okay, so I wanted to show you a few more examples. So for example, the N action, instead of looking at the SL2 action, if you take the N action on this bad example for SO2, it becomes a good example. Everything works. So it improves the situation there, and I'm 3 minutes over time, so let me stop. Thanks very much.
Great. Let's all thank Marc for a wonderful talk. So I got this hunch that maybe you're motivated by problems in A1 enumerative geometry, and if that's correct,
yeah,
you can comment on that.
Yeah, so yeah, I mean, the thing is, you have these beautiful techniques developed by Graeber, Pandurapandi, and others of using localization to calculate virtual fundamental classes. So the next step in this is to reprove their virtual localization theorem in this setting, which I think is, the problems are only basic and fundamental, so it shouldn't be a problem. And no, I mean, I think that's pretty clear to use their program, and it should work to prove their localization theorem, virtual localization theorem in this setting. And then you want to do examples. So the nicest example is you can do Donaldson-Thomas theory. So on all these Hilbert schemes of threefolds, you have you have a nice, perfect, even symmetric obstruction theory. And you can, it makes perfect sense to do this in this Witt ring setting. So you already have the foundations for what you might call a real Donaldson-Thomas theory. And it should be possible to use these localization techniques to actually make computation. So started to do that for P3, and it looks like the n squared localization, the n squared action you get by taking the SL2 squared action should be good for handling that. But it's still a little unclear. It works for degree 2, but it's not very. I have one Donaldson-Thomas invariant. So degree 1, you get 0 because there are no degree 1 fixed points. Right, this n squared action, you have sort of 2 skew lines, and SL2s acts on each of those, and the n acts by the torus action together with t goes to t inverse. So there are no fixed points for those actions, which is reasonable because the Euler characteristic of P3, the quadratic Euler characteristic is 0 in the Witt ring. It's 0 because it's an odd dimensional manifold. And you actually see that because there are no fixed points by the n squared action. And but if you have degree 2 things, of course, there are 2 fixed points. And so you should get a Donaldson invariant of 2, which I think is what 2 times the unit, which I think is what you get. And this agrees with the calculation. It's at least mod 2, it's equal to the one you get for the complex number. So hopefully it's correct.
Mark, I have a kind of a generic question.
Sure.
Suppose that you're looking at the action of SL2 on a Brouwer severity curve. So then now you have the field extension and you have
SL2 doesn't act on a Brouwer severity curve.
sorry?
Does SL2 act on it
Yeah.
acts on PGL2. It acts on the form of PGL2, but I don't think it descends to an action on the Brouwer severity curve. Because you don't have a torus. See, SL2 has a torus in it, a split torus, and the split torus won't act.
Oh, so the issue is that it's a non-split torus.
No, but SL2, if you have an SL2 action, then you have a split torus action, because the SL2 has a split torus in it.
All right, I just did the calculation too fast in my head. Sorry.
Yeah, you have a twisted form of SL2 will act. I mean, the units in the quaternion algebra will act on the Brouwer severity curve, but not SL2. So I don't know what the Witt theory, the equivariant Witt theory looks like for the units in the quaternion algebra. That would be interesting to compute, but I don't know how to do that.
Is it conceivable that with this type of methods, you could actually compute some Witt groups of schemes directly, not Witt-cohomology?
Well, I don't know. I didn't try to do that just because I don't have enough good. I mean, you see what the program, what the tape, how to run the tape. You need to know that the orbits that you're looking at have cohomology, which vanishes after you invert. So you need to get some idea of what the coefficient ring is, right?
Yes.
So you need to know what the Witt. You already need to know what the Witt groups of BSL2 is.
Yes.
So you need that. And once you have that, then you need to know you can find elements there which don't do too much damage on inverting them, but will kill non-trivial orbits in whatever setting you're looking at. So that would work, but you need to verify that. And so for the Witt theory, I haven't done that. I took the Witt-sheaf as really the simplest version of a interesting theory from the quadratic point of view. So I haven't gone any further with that, but it's certainly a nice thing to look at.
And maybe a question for, usually when you take the equivariant torus cohomology and you kill the coefficients in positive degree, you get the usual non-equivariant version. Is that still true in the setting and somehow? Or?
Yeah. I mean, that's, well, let's see. I think it depends. I mean, certainly it's true for, the classifying spaces. It's a computation. So, I mean, at least for BSL2, for BN, let's see what happens. Yeah, I think for BN, it also, if you kill all the Euler classes, I think you just get the theory of a point. So, but that's, yeah. Is that true? Probably it's true. No. I'm not sure though.
But I mean, not just for the equivariant cohomology of the point. I mean, for the spaces on which you're actually.
Right. No, I know what you mean. So I'm not sure. I haven't tried to do that.
Okay.
I mean, this residue theorem, I think of it more in practice. You get an answer in some localized theory, but you know that the answer comes from the constants anyway. So if you compute it, you'll see it's just a constant. It doesn't have anything in there, so you know where it comes from. So, I mean, in that sense, you see what I mean?
No.
You usually don't use it to compute the Euler class. You usually use it to compute the degree of the Euler class. And then you're back in the theory over a point. Right, you want to usually use it to compute the degree of something, not the class, but the degree of the class. And then you're over the point and you just look at it, you say, well, it's, you know, it's coming from the non-equivariant theory. So it has to be a constant when you take the degree. It has to not involve the Euler classes of the bundles. And that's what seems to happen in practice anyway. So I haven't, it's probably the right way to do it is what you're saying, but I haven't done that.
Okay. Thank you.
Just one question. Oh, sorry.
Yeah.
Go ahead.
Would you say a word
Okay,
about
so
the?
just one. Yeah, okay.
Go ahead. Go ahead, please.
Thanks. So can you say something about P? Is it explicit in the theorems? I mean, don't you have to?
Yeah, it's pretty explicit.
It's always a product of it's always a product of characteristic classes. You don't have to invert any two, for instance, or something like that.
Ah, that's a very good question. You do have to invert twos.
Ah,
right. Really annoying. So
that's very bad. Yes.
You win some, you lose some. So the point is for SL2, for SL2 to the n, the things that might involve a 2 are already 0. So things like even symmetric powers of the tautological representation, those already have 0 Euler class. So if you have to invert those, you're dead anyway. So you're inverting 0. And the ones that are non-zero will have coefficient 1 usually. So that's fine, but sometimes, you know, the whole thing blows up. When you use n, so I just say, you have these bundles O tilde of m, which come from the representation where the torus acts by t to the m, t to the minus m. It's a two-dimensional representation. And sigma acts by 0, 1, minus 1 to the m. So you see what happens when m is even, this matrix has determinant -1. And so it's not even in, you have to give a twist to the Witt-sheaf, which I didn't talk about, in order to even talk about those things. So if you take this Euler class of, let's say this, E tilde of 2, this might come up, right? This is what comes up in the sim2, in fact. If you take this thing, it's not even in the group you're talking about. But if you square it, you get 4e squared. So there's a 4. Okay, so that's what happens in this example of the, I said it was a good example for n, instead of SL2 acting on this P of sim2 of f minus P of sim of f, you have a good n action, but the classes you have to invert involve a 4. Well, it's a good point. I should have said that. So it's bad in the sense of general theory of the Witt ring, but if you at least get information for real embeddings. So okay, but that's what happens. I mean, you're kind of stuck. There's no way around it.
Well, unless it kind of formally cancels from a numerator and denominator, and that you're still allowed to do that cancellation. And speaking of formal,
yeah, you could make a guess, but you don't.
Well,
have
also, yeah, I was wondering about the examples you mentioned of Sabrina Pauli, because you know there are these beautiful cancellations that just occur, and then you magically get an integer, even though you're.
That's true. In those examples, the denominators don't involve any coefficients. The denominators look like products of the thing, EI squared minus EJ squared, things like that.
Would you say a word about what her examples are?
She did the example of lines in lines in projective space, or looking at lines on complete intersections, things like that. So in PN, where you take the degrees so that the you get finite, you know, the general one has finitely many lines. And
right.
The point is, when you're looking at, I'm using the affine notation, so you're looking at two planes in n+1 space. And let's take n+1 to be even, just for simplicity. Then you know, the fixed points, you just have finitely many fixed points just corresponding to the line span, you know, by x, you know, if I use 2i plus 1, x 2i plus 2, right? And then 0 elsewhere. So that gives you the ith line, so to speak. Well, maybe I should have used -1 and +1. 2. Sorry. So that gives you the ith line. So those are all the fixed points in the Grassmannian. And then the point is as I said before, the normal bundle is just the tangent bundle, but you know what the tangent bundle is at this point. The tangent bundle is your ambient space, A2n plus 1, with the SL 2 to the n acting modulo the line. This is the normal bundle at the line. It's Hom of Li into this thing. And so this splits up into a bunch of tensor, this gives you the fundamental representation in the ith factor, and this will be the sum of the fundamental representations in the other factors. And the tensor product of these two things gives you exactly this. So this will have Euler characteristic, will be equal to the product over all j not equal to I, but fixed I of EI squared minus EJ squared, because that's the Euler characteristic of a tensor product. And the numerator looks quite a bit different. It'll be the thing you get for the sim whatever. If you're looking at for a hypersurface of degree, with the right degree, I forget whatever the right degree is, say D, then you're looking at sim D of the fundamental representation, which has this D double factorial times the Euler, it'll be the ith Euler class. So that's the denominator. And the top one will be some D double factorial EI to some power, D plus 1 or something. And then you'll be divided by this product EI squared minus EJ squared. And when you take the sum of these over all the points, the numerator, I mean, there's a sign involved because depending on whether I is, you'll get plus or minus, and you have to orient things properly. And it turns out you just get this denominator back. So when you take the sum of all these things, it's just d factorial, double factorial. So that's one computation that she does. And then she does a bunch of other ones for not just hypersurfaces, but complete intersections.
Nice.
The complete intersection is basically the same computation. You just get the products of those, the double factorials.
So did I get the argument right? Is that more or less right? Or is that, or did you do it differently? Maybe you can tell us how you did it.
No, that was exactly right. I'm not sure about the exponent of the EI, but I don't know it right now. Yeah.
Yeah, it's probably
Maybe
not right.
I think there was like a 2 in there. There should be a factor 2 in it. Maybe I think it's 2d minus 2, but I'm not sure.
Oh, okay. Whatever.
Whatever.
Some exponent. Yeah,
So
it's the one that works.
So the real answer for complete intersection is a product of the D's involved in the, so there's a simple closed form answer for the Witt part. Because you know the complex answers in general, they're not, there's no closed form. They're hard to compute. I mean.
Yeah, these are easier.
So I did not, okay. So you're telling me that for the SIMD1, SIMD2, SIMD3, that I'll always get the product of the DI factorials with the,
well, you tell
oh, you know what? Okay. Please go ahead.
Sabrina, you're up. Is that what you get?
Oh, yeah. You're right.
I get it.
Exactly this, yes.
Right. So for a complete intersection of degrees D1 up to DR, you get the product DI.
Thanks a lot.
So this is by Sabrina Pauli. Oh, who's next? How many?
Very happy to hear about that competition. Looks great. Any other questions? Doesn't seem to be the case. So let's thank Marc once again for a wonderful talk.
Yeah, thanks very much for having me here. Sorry I couldn't be there in person. It was a real pleasure to see you all, only virtual. Bye-bye.